Hello my dear children of class 12 science. Today we do continue with the chapter, one of the chapter that is diffraction of light, and this is the last chapter as for reduced syllabus. Okay, and in today's class we start with the topic that is variation in the intensity of diffraction pattern with angular position in a single slit. And children, this chapter we have already started in last class only. Okay, and in today's class we complete this chapter. So basically this topic which I said just now is important for your examination also. Okay, and in this case we plot a graph. Actually we plot a graph of intensity versus angular position or angle of diffraction, okay, produced by all the secondary maxima and minima. And this graph is called intensity of diffraction pattern with angular position in a single slit. Now, as you know, to plot the graph, let me just take the condition, children, that now there is a condition for secondary minima. And you know what is the condition for secondary minima? The condition is, since E sin theta m equals to plus minus m lambda. See, I have written the expression out here. E sin theta m equals to m lambda equal. Okay, this is the condition for secondary minima. Secondary what? Minima. Now to get secondary minima, the path difference, this is path difference, E sin theta m is the path difference, must be equals to plus minus m lambda. And you know why plus minus sign out here? Plus minus means because your secondary minima is formed on both sides of central maximum. Okay, so if E sin theta m equals to plus minus m lambda, then I write this expression even as sin theta m equals to plus minus m lambda by E. So I'll take this E in the denominator. Now in this expression, theta m is the angle made by any mth secondary minima with the central maximum. This is the angle, theta m is the angle made by mth secondary minimum with the central maximum. But basically in case of diffraction pattern observed by the phonophore in due to single slit, this angle secondary minima which is formed on the screen, okay, this secondary minima which are formed on the screen, sorry, are very small angle. They make very small angle. So it means that this angle theta m is very small. Now basically experimentally theta m are, these angles are very small. So if theta m is very small, then you know the condition we can write out here is sin theta m is nearly equals to theta m. So in mathematics, if theta m is very small, then sin of theta m can be written with theta m with the limit. Now I write the same expression out here also. Therefore sin theta m I can write as theta m, which is equals to plus minus m lambda by what? E. M lambda by what? E. Now this theta m equals to plus minus m lambda by E makes that we can find any secondary minima, the angle made by any secondary minima, sorry, with the what maximum? Central maximum. So for that, let me just do this way. Therefore I write down theta 1. If I write m as 1, then it will be theta 1, and theta 1 equals to plus minus lambda by E. Because if I put m equals to 1 out here, it will be 1 into lambda means lambda, so lambda by E. So theta 1 equals to plus minus lambda by E. Similarly, if I put m equals to 2, m equals to 2, then it will be plus minus 2 lambda by what? E. Similarly, if I put m equals to 3, then it will be theta 3, and I don't theta 3, no problem, plus minus 3 lambda by E. So it will go on like this. This means this theta 1 is the angle made by first secondary minimum with a central maximum. Theta 2 is the angle made by second secondary minimum with the central maximum. And theta 3 is the angle made by third secondary minimum with the central maximum. So in this way, any secondary minimum makes certain angle with the central maximum. And this angle is measured by this. So with this angle now, we can plot a graph, and this graph is called intensity of diffraction pattern with angular position in a single slit. Now in order to know what is the nature of graph, it has already plotted out here. So this is the graph that we are actually going to plot, but the nature has been drawn only. So let me explain it. So in this graph we take x-axis from this point O as origin, and but in diffraction pattern this origin acts as central position in diffraction pattern. Now y-axis is taken as intensity, and x-axis we take as angular position. So with 0 on the positive side it is theta m, on the negative side is minus theta m. That means this angle can be positive on the right hand side and negative on the which side? Left hand side. But as for the photographer which observed the diffraction pattern on the screen due to single slit, he observed the diffraction pattern in such a manner so that the center fringe, which was found to be a maximum intensity, center fringe was found to be to have what intensity? Maximum intensity. That's why in case of diffraction pattern, the maximum intensity is always with central fringe. So this is the central fringe. Okay, this is the what? Central fringe. This is the central bright band. This is the central bright band. Also we can use a central or principal maximum, which has maximum intensity. The intensity of a central fringe is maximum, and that is 1. But after that central maximum, this become minimum, and this minimum is called first secondary minimum. First secondary what? Minimum. Because you know that on either side of central maximum, the secondary minimums are formed, and this is the first secondary minimum, and this is also the first secondary minimum. This is also the what? First secondary minimum, which means first secondary minimum are always formed on either side of central maximum, and central maximum has maximum intensity. Okay, now this is first secondary minimum. The first secondary minimum makes certain angle with the central maximum. This is the angle, and this angle is actually theta 1. With the central maximum, this angle is what? Theta 1. And this angle which is made by the first secondary minimum on positive side is lambda by e. This angle will be lambda by e. On the negative side it will be minus lambda by e. This angle theta 1 is lambda by e on the positive side, and this side also it form angle. I draw a dotted line this way, and this angle is also theta 1 but of negative side. So these are the angular width of first secondary minimum with the central maximum. Then we have this one. This is the first secondary maximum. This is the first secondary maximum. Now this first secondary maximum has intensity less than central maximum, and even the width also decreases. See, central maximum has broader width. Then when you move from first central maximum to the secondary maximum, their width simply decreases. Okay, so intensity decreases and the width also decreases. Then this minimum is called second secondary minimum. This is called, width is called second secondary minimum. Secondary what? Minimum. Minimum. And this is given by 2 lambda by e. This is given by 2 lambda by e. And then the same side, on the left hand side, this is central maximum. This is what? First secondary maximum. First secondary maximum. Then after this is second secondary minimum. So this is secondary what? Minimum. And second secondary minimum is also given by minus 2 lambda by what? E. So in this way, children, we can do for any minimum. Then after what we come? This is second secondary maximum. This is second secondary maximum. So in this way, what happened? Secondary minimum, maximum will form on both sides of central maximum. But what will be observed out here? The intensity keep on decreasing. See, decreases, and the width also decreases. The width also decreases. Similarly, this is third secondary maximum, a minimum, which is given by 3 lambda by e. This is given by 4 lambda by e. So we can see all minimums like this. So this is first secondary minimum, second secondary minimum, third secondary minimum, fourth secondary minimum. It goes on. In the left hand side also, it will be first secondary minimum, second secondary minimum, third secondary minimum, which is given 3 lambda by e with minus sign, and goes on. So in this way, we can see the formation of diffraction pattern with all secondary minima and what? Maximum on both sides of central maximum. But as I said just now, when we move from central maximum to both sides, the width of intensity of secondary maxima will decreases, and the width also decreases. And this graph show that all fringes which are formed are not of equal width. and not about with equal width. So this is the intensity intensity of diffraction pattern with angular position in a single slit. But children, from this graph also we measure the angular width. Yes, we have already measured the angular width of center maximum. This is angular width. This is angular width of center maximum, and we do the numerical of this also. And this angular width will be 2 theta 1. 2 theta 1 is the angular width of center maximum, and that is 2 lambda by E. This width is theta 1, that is lambda by E. This is also lambda by E, neglecting minus sign. Okay, angle is angle. Okay, so lambda by E and lambda by E, if you double it will be 2 lambda by E. So when we measure the angular width of center maximum is measured by 2 lambda by E. But remember this angle we measure when we consider angle is very small, and we measure this angle in what? Radian. Now we have similar graph that we can plot the intensity of light with path difference for Fraunhofer diffraction due to single slit. The same graph that you can see, but only thing is that this angle is replaced by the path difference. So to understand the graph, this nature of graph is same, exactly same. Okay, exactly same, but only thing is that this graph which we plot out here is the graph between intensity and path difference. So I replace this angular position by what? Path difference. And in order to measure this, so let me just follow this one. The path difference is sin theta m equals to plus minus m lambda. So what is this? This is the path difference for mth secondary minimum. Mth secondary minimum. So if I put m equals to 1, so E sin theta 1 equals to plus minus lambda. And this is the path difference for first secondary minimum. Similarly, if I put m equals to 2 out there, so E sin theta 2 equals to plus minus 2 lambda. So it will go on and on. That means with this path difference, we can plot a graph. So this is for first secondary what? Minimum. Positive side, it will be, the path difference will be what? Lambda only. Now this is the second secondary minimum. On the right hand side, your path difference is what? 2 lambda. Similarly, this is the third secondary minimum. The path difference will be 3 lambda. So on the left hand side also, this is the center maximum or principal maximum, which has intensity maximum. And this is first secondary minimum. On the left hand side, the path difference is minus lambda. Similarly, you can see this is second secondary minimum. On the negative side, the path difference is minus 2 lambda. This is the third secondary minimum. On the left hand side, the path difference is minus 3 lambda. So in this way, we can plot the intensity versus path difference graph on both sides of center maximum with positive side as well as negative side. But children, just compare these two graphs. These two graphs nature is same. Only difference is that this graph is intensity versus angular position, and this is intensity versus path difference graph. Whereas in this graph also we have center maximum which has maximum width. Then when we move from center maximum to on both sides, the width decreases and the intensity also decreases. Okay, so this makes the explanation, the graphical representation, especially to understand diffraction pattern due to single slit. And this diffraction pattern due to single slit is expressed by the two different graphs which I have explained: intensity versus angular position and intensity versus path difference. First secondary minimum, second secondary minimum, third secondary minimum. First secondary maximum, second secondary maximum, it will go on and on. On both sides, what? Center maximum. So this is the explanation which I have done based on diffraction pattern. Now children, we solve some numerical problem, and the numerical problem we solve in the next YouTube video.